Welcome to the deep dive. We got a really interesting request to unpack this talk by Grant Sanderson.
Oh, yeah, the one about how large language models work.
Exactly. He dives into transformers, especially that attention thing everyone's talking about. So we're diving deep. Tokenization, embeddings, attention.
All the good stuff.
We're going to help you get a feel for how these AI giants actually think.
Yeah, it's really something. Sanderson does a great job with the analogies and the visuals.
Right.
But we're going to try and unpack some of the math behind it, too.
I love it. No smoke and mirrors here. Just pure mathematical muscle.
Exactly.
So Sanderson starts by talking about how these models, process text.
Right.
And it all begins with tokenization. I got to admit, the first time I heard that word, I thought it was something you'd use at an arcade.
Uh-huh. Yeah, I can see that. But in this world, tokenization basically means breaking down text into those smaller chunks, those tokens. They're usually words, but sometimes they're bits of words or even punctuation marks. It's like, think of it like taking apart a sentence and turning each piece into a Lego block.
Okay, Lego blocks. Got it.
Yeah.
But why not just use individual letters? That seems way simpler, at first glance.
That's a really good question, and it seems intuitive, right? But think about it. Imagine the model trying to learn what a word means letter by letter every single time.
Oh, yeah.
It would be like teaching a kid to read without ever showing them whole words.
Right.
Plus, the model has to keep track of so much text.
So much.
Using words or chunks as tokens really helps it, stay efficient.
Makes sense.
Yeah.
So it's about giving the AI a head start.
Yeah.
Now, Sanderson mentioned something called byte pair encoding, which sounds like it's striking a balance there.
Byte pair encoding is super clever. It basically looks at all the text the model is learning from and figures out, the most frequent chunks of letters.
Oh.
And those become tokens. So it can handle, the common words, but also those weird little word bits efficiently.
Okay. Now we're cooking. So we've got our Lego blocks, our tokens, and then we embed them.
Yeah.
Now that sounds almost mystical.
Yeah.
It's like turning a word into, its mathematical soul.
It is kind of mind-blowing. So each token, each one, gets matched with a vector,
Uh-huh.
which is just a fancy word for a list of numbers. And this vector, it represents the word's meaning in this multidimensional space.
Okay.
And it's this embedding space where things get really interesting.
I love how Sanderson shows how words with, similar meanings end up clumped together in this space. It's like the model's making its own little map of meaning.
Exactly. It's creating its own understanding of relationships between words just based on the data it's seen.
That's so cool.
Yeah. And he even gives that classic example, king, man plus woman, queen.
Oh, yeah.
It's like the model figured out a gender direction in the embedding space.
Wait, hold on. The model it did math and understood gender.
Pretty much. It's figuring out these relationships just by crunching numbers.
Okay, that has officially blown my mind.
Yeah. It's wild. And get this, GPT-3, one of the big ones out there, it uses a 12,288 dimensional embedding space.
12,000 dimensions.
Yeah.
I can barely visualize 3. My brain hurts.
Right. No wonder these things need so much computing power.
It's crazy.
We're talking about capturing, all the nuances of language in a massive mathematical structure.
Yeah.
It's pretty amazing.
Oh, wait. So if each word's got this vector, its meaning, does it stay the same, forever?
Nope. And this is where it gets even cooler.
Oh, no.
A token's embedding, it changes as the model processes the words around it. So remember Sanderson's example with the word one in Robert Frost's poem?
The road not taken.
Yeah.
Yeah. I remember
That first one, it just means the number, right?
Right.
But as the model reads the whole line, the embedding for one, it starts to absorb all this extra meaning.
Oh, wow.
About choice, about taking a unique path.
Well, it's not just a dictionary definition. It's like the model's actually understanding the feeling of the word in that context.
It really is. It's like the meaning gets richer based on the company it keeps.
Which makes you wonder, how much can these models really hold?
Right.
Sanderson mentioned something about high-dimensional spaces, like having tons of almost orthogonal vectors. I'll admit, that one went a little over my head.
It's a bit of a head-scratcher for sure. But basically, imagine you can fit way more lines that are almost perpendicular to each other in a high-dimensional space compared to, say, just a flat piece of paper.
Okay.
So it's not just about stuffing in as many words as possible. It's about capturing all those intricate relationships between them.
That's incredible.
It is. It's like weaving this tapestry of meaning where each thread, each vector contributes to the richness of the whole thing.
Okay, so we've got our tokens, we've embedded them in this mind-boggling multi-dimensional space.
Right.
But how do they actually make sense of the text? That's where the heart of it all comes in. The attention mechanism.
The attention mechanism. This is like the secret sauce. It's what makes Transformers so special.
I love how Sanderson talks about words like talking to each other to, refine their meaning based on context. But how does that actually play out, like mathematically? He throws in these query, key, and value matrices.
Yeah.
And those always trip me up.
I know, they sound pretty technical, but think of it this way. Each word has a question it wants to ask.
Okay.
That's its query. The other words, they have potential answers.
Okay.
Those are their keys. And the value matrix, that's like the actual information that gets used to update a word's meaning based on the whole conversation.
So the query is like searching for information and the key is like holding the possible answer.
Yeah, it's like a cosmic game of question and answer.
I love it.
And here's where the magic happens. The model calculates the dot product between each query and each key.
Ooh.
And that dot product, it tells us how much those two words are like aligned. You get a high dot product. They're basically soulmates. Low dot product, not so much.
I love those visuals Sanderson uses, like where the dots are getting bigger or smaller to show like how much attention each word's giving to the others.
Oh, yeah, it really helps to see it, right?
It's so cool.
It's like they're having their own little conversations, but we can't just use those dot products directly.
Right.
That's where the softmax function comes in.
Uh-oh, more jargon.
Think of it like a popularity contest for word connections.
Okay, I like that.
Softmax makes sure that all the weights are between 0 and 1 and that they all add up to 1.
Gotcha.
So it creates a probability distribution.
So it's like each word gets a weighted vote based on how relevant it is to the others.
Yeah. Democracy in action, but for language models.
Exactly.
And then these weights, they get used to create a weighted sum of the values for each token. And that sum gets added to the original embedding. So it's like refining its meaning based on the whole sentence.
So the attention mechanism is like taking those initial embeddings, those kind of basic meanings, and like giving them this serious upgrade.
Exactly. They become context aware. Their meanings are like enriched by their relationship with all the other words.
Oh.
It's a beautiful thing.
Mind-blowing stuff.
It is. And we're just getting started. This whole process, it happens for every single token, creating this incredible dynamic web of connected meanings. But there's a cool trick during training. It's called masking attention.
Masking attention. Sounds kind of secretive.
It is a bit. But remember how the model's learning by trying to predict the next word in a sequence?
Right.
Well, we can't let future words influence the past during training.
So we're keeping things fair.
Exactly. It's like preventing the model from peeking at the back of the book during a test.
Good sportsmanship, even for AI. I like that.
Right. So masking attention, it ensures that the model learns to predict the next token only using the words that came before it.
So it's really learning like organically from the text as it goes.
It really is.
That's amazing.
It's crucial for effective training.
It's incredible how much thought goes into like designing these models. It's almost like choreographing like a dance.
Oh, yeah.
Of numbers and algorithms.
Mm-hmm.
But Sanderson points out that this attention pattern, it can get really big, really fast. Like it grows quadratically with the context size,
Yeah,
right?
I got it.
That's a great point.
Isn't that a problem when we're dealing with longer and longer pieces of text?
It can be. It can be a bottleneck, yeah, especially with longer text. That's why, models with larger context windows, they often use these clever caching tricks to avoid recalculating the same attention patterns over and over, especially during, text generation. It's all about efficiency.
Oh, that makes sense. So they're making things run smoother, without sacrificing accuracy.
Exactly. It's all about finding that sweet spot between keeping the model efficient and maintaining its ability to understand and generate coherent text.
And I bet that's why, like, going back to that question of using individual characters as tokens, that would just make that context size explode.
Yeah.
And then the quadratic growth would be a real headache.
Exactly. It's all a balancing act between the token size, the computational efficiency, and making sure the model can actually, grasp the meaning effectively. But wait, there's more. We've been talking about a single head of attention.
Oh, no.
But these models, they often use multi-headed attention. Like it's like having multiple perspectives on the same text.
Multi-headed attention.
Yeah.
Okay, now we're getting seriously advanced.
It's pretty wild to think about, right? Like all those calculations scaled up to billions of parameters.
Yeah.
It can somehow capture these like abstract ideas and subtle meanings,
I think that's all right.
It's no wonder people are both like excited and a little nervous about these models.
Right. It's totally mind-blowing. We've covered like tokenization embeddings and how those tokens, talk to each other using the attention mechanism.
Yeah.
But honestly, the sheer size of these models still kind of boggles my mind.
It is massive.
Sanderson mentioned that GPT-3 has like 96 layers,
Oh, yeah.
each with multiple attention heads. That's a lot of processing going on.
It is a lot going on. And that multi-layered structure is really key to how the model learns these increasingly complex ideas, from the text.
Yeah.
Imagine it like building a pyramid.
Okay.
The first layer, maybe it just figures out, basic word meanings. The next layer uses those to understand phrases, then sentences, and so on.
Okay.
Building up to these really sophisticated interpretations.
So it's like this hierarchy of understanding.
Yeah.
With each layer getting like smarter and smarter.
Exactly. And within each layer, you've got those multi-headed attention mechanisms, working their magic in parallel.
Yeah.
One might be focused on grammar.
Okay.
Another on like relationships between words. Another on long-range connections between ideas.
Oh, wow.
It's like having a whole team of specialists analyzing the text from different angles.
That's really cool. So Sanderson pointed out that like this deep layered architecture, combined with the attention mechanism, makes transformers incredibly good at parallel processing, right?
Oh, yeah, for sure.
They can like zoom through information way faster than we can.
Way faster.
Since us humans, we tend to read things word by word.
Right.
Like it's 1999.
One word at a time.
Yeah, exactly.
Like we're stuck in dial-up.
I know.
And that parallel processing, it's a lifesaver when it comes to training these models.
Right.
Imagine trying to read the entire internet.
Oh my gosh.
Word by word.
I'd be there for centuries.
It would take forever. But transformers can process huge chunks of text simultaneously.
Oh, wow.
Making the whole training process way more efficient.
It's like they have a super-powered reading brain.
Yeah.
Absorbing information at warp speed.
Exactly. That's a great way to put it.
No wonder transformers have like totally revolutionized the field of natural language processing.
Oh, they have for sure. The combination of that deep layered architecture, the attention mechanism, and that parallel processing power, it's led to breakthroughs in all sorts of areas. It's crazy. From translating languages to writing different kinds of creative content. It's amazing to see what they can do.
Okay, so we've got these super powerful models that can write poems, translate languages, answer questions.
Yeah.
It's almost like they, understand and generate human-like text.
Right.
But Sanderson mentioned that training them to predict the next word in a sequence, what he called pre-training, is just the first step.
Right.
What happens after that?
Yeah, that's a great question.
How do they go from being like good with words
Yeah.
to being like helpful in specific ways?
That's where fine-tuning comes in.
Fine-tuning. Is that like sending them to finishing school?
Kind of. Think of it like taking a general language whiz
Okay.
and helping them specialize.
Got it.
It involves giving the model extra training data and feedback that's tailored to the specific task we want it to be good at.
So if we wanted like a chat bot,
We
might train it on conversations between real people. So it gets the hang of how like dialogue works and learns to respond in a natural way.
You got it. Or for a question answering system, we'd train it on tons of questions and answers.
Right.
So it learns how to find the right info and give accurate responses.
Fine-tuning sounds crucial. It's like taking this raw talent and like shaping it to become a true expert.
It really is. And often that fine-tuning process involves feedback from humans.
Oh, interesting.
So there's this element of human intelligence kind of guiding the model's learning and refining its performance.
So it's not just about like raw computing power,
Right.
but also about human guidance to help the model really shine.
Exactly. It's a partnership.
I like that. Now, Sanderson also made a point of saying that transformers aren't just limited to words.
Oh, that's right.
He talked about how researchers have used them for images.
Uh-huh.
It's even like mixing different types of data. That sounds like a whole new level of AI.
It is. It's really exciting. Being able to process different kinds of information using the same underlying architecture opens up so many possibilities. It's crazy.
Imagine models that understand not just what we say,
Right.
but also what we see and hear.
Whoa.
We might be able to create a more holistic, integrated kind of artificial intelligence.
That's a wild thought.
Yeah.
It makes you wonder, like, what applications these models could have beyond just language.
Yeah.
Could they analyze medical images?
Potentially.
Compose music?
Maybe.
Maybe even control robots? The possibilities are mind-boggling.
They really are. Researchers are exploring all sorts of exciting avenues.
That's so cool.
We're in the midst of a real AI revolution. It's an incredible time to be paying attention to this field.
I know. This deep dive into transformers and attention has been eye-opening to say the least.
I agree.
It's mind-blowing how these mathematical operations, combined with clever design choices
Yeah.
and tons of data have created models that seem to mimic human understanding.
It is pretty
It's
amazing.
almost like we're seeing the birth of a new kind of intelligence.
It really is a remarkable feat of engineering and creativity. And while we've, peeled back some of the layers
Yeah.
and started to understand how these models work,
Right.
there's still so much more to explore.
Yeah.
AI is evolving so rapidly,
Mm.
and the future holds, endless possibilities.
I completely agree. This feels like just the beginning of our exploration.
Yeah.
But before we get ahead of ourselves,
Okay.
let's take a moment for our listener to process all of this incredible information.
Yeah. Good idea.
In the final part of our deep dive,
Okay.
we'll explore what all of this means for the future. What are the implications of these powerful models? What does it mean for us as a society? We'll tackle those big questions and more right after this.
Welcome back to our deep dive into transformers and attention. We've been on quite a journey exploring the nuts and bolts of these powerful language models,
It's been fun.
but now it's time to kind of tackle the big picture.
The big picture, yeah.
What does it all mean?
Right. It's time to shift gears a bit. We've seen how these models work, but now we need to step back and think about, the implications of having these incredibly capable AI systems out in the world.
It feels like we've cracked open the hood, we've seen the engine running,
Uh-huh.
but now we need to figure out where this car can take us and, make sure we've got a good driver.
Exactly. And one of the most important things to consider is responsibility. As these models become more powerful, more common,
Yeah.
it's crucial to make sure they're used ethically and for good.
It's like giving someone a super powerful tool, right?
Yeah.
You really want to make sure they know how to use it safely and for the right reasons.
Yeah.
It's both exciting and a little daunting, honestly.
It is. And another big challenge is this issue of transparency.
Hmm.
These models can be incredibly complex
Oh, yeah.
with billions of parameters, all these intricate mathematical calculations.
That's a lot.
It can be really hard to understand why they make the decisions they do.
It's like trying to understand a brilliant artist's work without ever seeing their process
Right.
or knowing their influences.
Hmm.
You can appreciate the final product, but you're left wondering, how did they get there?
Right. That's a great analogy. And without that transparency, it's hard to build trust. If we can't explain how these models work,
Yeah.
it's hard to know, if they're making decisions that are fair, that are unbiased, or to identify problems if they arise and, actually fix them.
We need to be able to, look under the hood,
We do.
so to speak, to make sure everything's running, smoothly and ethically.
Yeah.
It's a challenge, but one that feels absolutely essential.
It's a crucial challenge, and it's something that, researchers are working on right now,
Okay, good.
developing tools and techniques to make these models more transparent, more explainable.
That's really good to hear. Now, Sanderson's talk, really focused on those inner workings of transformers, but he ended with this kind of thought-provoking question. How could we apply these attention mechanisms to other fields?
Oh, yeah.
And, what ethical considerations pop up as these models keep getting more and more powerful?
Those are the million-dollar questions. The attention mechanism, it's all about focusing on what's important.
Yeah.
Making connections between different pieces of information.
Right?
And those principles, they could potentially be applied to all sorts of areas beyond just language.
Imagine using attention mechanisms in medical diagnosis.
Yeah.
Doctors could analyze huge amounts of patient data
Yeah.
to spot subtle patterns, make more accurate predictions, maybe even catch diseases earlier.
Early detection is key.
Right. Or think of
Oh.
designing smarter transportation systems that use attention to optimize traffic flow based on, real-time information.
Right. Make our commutes less of a headache.
Exactly. The possibilities seem almost endless.
Almost endless.
But as we start to, explore these new frontiers, it's crucial to keep those ethical considerations front and center.
Absolutely front and center.
Right. We need to make sure these powerful tools are used for good, to benefit humanity,
Yeah.
and to, help us address some of the challenges that we face.
I agree.
This deep dive has been an incredible journey. We've gone from understanding those basic building blocks of these models to pondering their impact on society.
It's been quite a ride.
It has. It has. It's clear that transformers and attention mechanisms they're a game changer.
Oh, yeah.
And it feels like we're just at the beginning
That's the begin.
of this incredible journey of exploration and discovery.
Totally agree.
So on that note,
Okay.
we hope this deep dive has sparked your own curiosity. Keep asking questions, keep learning, and keep exploring this amazing world of artificial intelligence.
You never know what you might discover.
That's a perfect note to end on. Thanks for joining us on this deep dive into transformers and attention. Until next time, keep those brains buzzing.